All right, this is the last part for this this section of the chapter, and it's an optional bit. It's just the proof of why the power rule works. And so before we prove this, I want to review what x plus h raised to various powers is. Of course, anything raised to the 0 power is 1. X plus h to the first power is x plus h. To get x plus h squared, you do x squared, then you take twice the product of these, so you get 2xh, then you get h squared. Now, when you're raising this to higher powers, what you need to do is use Pascal's triangle, binomial theorem. I've already got several parts of Pascal's triangle drawn, but what this is, you start with the 1, and then for each additional number, you add these two numbers above to get what goes in this block. So here we get 6, then we get 5 plus 10 is 15, 20, 15, 6, and 1. So for instance, if I wanted to do, say, x plus h to the 4th power, what I would do is I'd come over here to this 4th line, and I would get x to the 4th. These numbers here are my coefficients. So the next one is going to be plus 4x to the 3rd h plus 6x squared h squared. Notice each time I go from one term to the next, I'm taking one of the powers off of x and putting it onto h. So let's move this over so I've got enough space. So 6, next up is 4xh cubed, then plus 1h to the 4th. So you can do that. And in general, if you have x plus h to the n, what you've got here is x to the n, and you've got n times x to the n minus 1 times h. And then you've got some smaller terms with h raised to a power bigger than 1. Like over here, notice x plus h to the 4th. You've got x to the 4th, 4x cubed h. Then all the rest of these have h raised to a power that's bigger than 1. Now that matters because when we go and do the limit, what we're going to do down here is we're going to do the limit of this. We're going to find the derivative by using a limit. So what you get here is the limit as h goes to 0 of f of x plus h, that's x to the n, so, or x plus h to the n, so you get x to the n plus n times x to the n minus 1 times h plus, now this next one is going to have some coefficient that we got off of Pascal's triangle, but it's going to be x to the n minus 2 times h squared plus something times x to the n minus 3 times h cubed. All the rest of these are going to have h's in them, raised to big powers. So let's do this. This is x. Oh, I left off something important here. At the end, this is, let's see, this bit here, this is f of x plus h. Then I've got to subtract off f of x, which was just x to the n. So what I wind up with down here is x to the n plus nx to the n minus 1 times h plus, now out of here I'm going to factor out my h squared. So it's going to be h squared times some stuff. I don't even really care what that stuff is. It's just h squared times some stuff. All right. And now when we cancel things, the x to the n's cancel. And what we're left with is limit of, as h goes to 0, of nx to the n minus 1 h plus h squared times some stuff over h. All right, now we can cancel the h's. We're left with nx to the n minus 1 plus h times the stuff, and that canceled with the h on bottom. All right, now here's the cool part. The h gets replaced with 0. So this bit right here becomes 0. What we're left with is just nx to the n minus 1 plus 0 times the stuff. So that's just nx to the n minus 1. So that's how we get the power rule. It says if the derivative, well, it says the derivative of x to the n is nx to the n minus 1. That proves it when n is a positive integer. We're not going to prove it for other values, but it works for any value of n.